Okay, so I guess before I start, does anyone have any question that want me to talk about? No? Okay, so what we did last time. So today we're going to finish spectral graph theory, and then we're going to start with the part on parsimony, and we're basically not going to talk at all about sparsity or low rank matrices today. We're going to give just I'm going to describe just the very basics of something called finite frame theory, which is like a very nice language to then talk about these things. Okay, so we're going to do some interesting theorems in spectral graph theory, and then we're going to set up the mathematical language for this so-called finite dimensional frame theory. Okay, so what we saw last time, right? So we had a graph. Okay, let's put the players in. So I have a graph with vertices and edges, right? We had the adjacency, right? So A is its adjacency matrix, and we defined the graph Laplacian, right? Was equal to the degree minus A. Okay, and basically what we showed, right? We showed basically the following. I think I now can't remember, but I think I might have not finished fully the proof of this. But it was that lambda 2 of L was equal to 0 if and only if the graph is disconnected. Okay. So I think what we did, so last time, the proof that we did was we did this implication, right? So this was last week. Okay, the other implication is actually trivial, right? So I'll just do it now. So if G is, just as a warm up, so if G is disconnected, then this means there exists, right? So let's prove this. Okay? So if G is disconnected, okay, let me be a bit more. Okay, so if G is disconnected, right? What does this mean? This means there exists S and S complement, non-trivial, like, right? Non-trivial. By non-trivial, what I mean is like a partition that's non-trivial is just one where you're neither the empty set nor the whole thing. Okay, now it's simple. So just take a vector y. Say that. So just take a vector y that say 1 in S. Right. So the indicator vector of S. Okay, I should say such that S and S complement are not connected, right? That's the point. Right, where SC means all the edges that are, all the vertices that are in V, but not in S. Okay? So now just take Y being one, the indicator vector of the set. Then if you have that, then, okay, so let's see what, first of all, so Y is not a multiple, okay, is not linearly dependent, or I should, okay, Y and the whole one's vector, right? This being the whole one's vector, are not linearly dependent. Right? It's a fact, right? Like, I mean, depending what language you like, but right, Y is not equal to alpha times 1 for some alpha. Right? It would be the case where, remember, this one is the O1's vector. Right? So, let me go a bit. Right? This is the, right, the whole one's vector. Okay? So then, this is not, Y and 1 are not linearly dependent. So in particular, the span, they span a two-dimensional space, right? So span of Y and 1 is two-dimensional, right? Okay, so this is fact number 1. Fact number 2, right, so fact number 2, the if I take y transpose L y, right, then what is this? Let's write it out. We saw this before. This is the sum over all edges of just yi minus yj squared. Right? But because there is no edges in between, right? There is no edges that ever gets a 1 and a 0. All the edges are either within S or within S complement. So every single edge, yi is the same as yj. Okay, right? Because you either have that if ij is an edge, either both of them are in S or both of them are not in S, right? The picture to have in mind is you have a graph G, you have your set S, you have your set S complement, right? And being disconnected means there is no edge in between. There's lots of potential edges here, but there's absolutely no edge in between, right? That's what disconnected means. And so this means that there is never, right? There is, this term is never non-zero for an edge, right? You either get 0, minus 0, or get 1 minus 1, so this is 0, okay? So now, of course, because, right? Because L, I mean, we saw the same thing for the whole one's vector, but because L is positive semi-definite, and y transpose Ly is 0, then it must be that Ly is also 0, right? We did the same thing with the whole one's vector. I mean, you can just take, say, right? You can just write L in, take what's called its square root, right? Just write in the spectral decomposition and then split half to each side. Okay? Or its Koleski decomposition, right? I mean, there's many ways of doing this. Then this means that both, one is, we know, in the kernel of L, y is also in the kernel of L, right? Their span is at least two-dimensional, so the kernel of L, the dimension of the kernel of L, needs to be at least 2, right? So what does this mean? This means that the second eigenvalue of L is for sure 0, right? And this is the proof. I mean, there's quite a bit that needs to write, but there's really nothing to it. Okay, so this is what I didn't have time to do last week, but we finished it now. And now we're going to do something much more interesting, which is the following. What if okay, so now let's go into something more interesting. Okay, and I posted the notes on the forum in case I know that sometimes when you're following, like I scroll up and down and so on, it might be useful to have the notes next to you. Just download them from the forum, and they're might vary slightly, but they'll be more or less what I write. Okay, so the question we're gonna ask ourselves is there a relation? So what we proved, right? Let's put the theorem again here, right? Because this is so useful. So G is disconnected, right? If and only if the second eigenvalue of L is 0. Why is this such an important or interesting theorem? Because it's relating the spectrum of the graph with something about its geometry, right? This is a property about is a spectral property. This is a geometric property, right? And so this is the core of something called spectral graph theory, right? Is the fact that these relationships exist, right? And that networks can be understood by looking at the spectrum of matrices that you can create with them. I mean, a priori, this would not be clear, like not intuitive at all, I would say. But this is the first theorem that shows you this. But of course, most like graphs that are disconnected are not so interesting, right? Maybe more interesting are graphs that are almost disconnected, right? They maybe have two very strong components, or what we sometimes call communities, right? Maybe there's many connections like this, many like this, and then there's just one or another across. And maybe it's two communities are very connected and very little across. And so the natural question, of course, is there a soft version of this, right? Is it true that G almost disconnected will be related to lambda 2 of L being almost 0? Right? This is the question that we want to answer today. Again, this is a much deeper statement. Okay, so maybe I should say that all our objects here are finite. So it's kind of obvious that such a relation must exist. But the point is, I want this relation not to depend on n, right? I'm sure you can come up, I'm sure one could come up very, very easily with some inequality that shows that if one is really, really tiny, the other also. But the point is that if depends on the number of vertices, then it's really not a very useful relationship. I somehow want a relationship between these two things that doesn't depend on the size of the network, right? A really geometric property. Okay, I mean, basically what I'm trying to say is, if you take an n by n graphs, there's only finite number of them, right? So for all the graphs that are connected, there's only one smallest possible eigenvalue they can have, because it's a finite number. You could take just the minimum among all of them, right? So because of this, you could very easily get sort of useless relations of this type, right? Just in virtue of this fact. But I want somehow this relationship not to depend on n. Okay, so such a relationship, this has a name, and it's known as Cheeger's inequality. So Cheeger's inequality gives a relationship of this type, and we're going to prove a side to it. Like, we're going to prove one of the sides of it. Okay? And so, in order to prove a statement like this, it's going to help to normalize the Laplacian slightly differently. Okay, so it's going to help to consider a normalized version of the Laplacian. Normalized. Because we're going to consider almost disconnected. We're going to measure cuts, how many edges get cut, also in a normalized way, and this sort of takes away the dimensions in a nice way. So I'm going to define the normalized Laplacian in the following way. Hg is equal to, so I want it to still be symmetric, so I hit it, I basically want to divide by the degree, but I want to divide all in one side, because then they might not be self-adjoint, so I'm going to divide half of it in each side. Okay, this is the so-called normalized Laplacian. Okay, maybe I should make a note that we assume, let's assume there are no isolated nodes. I mean, in fact, we're really interested is in the case where the graph is not even disconnected, right? Because when it's disconnected, we sort of already understand. Right, if there's isolated nodes, then some of these degrees might be zero, and then it's kind of right, talking about the inverse of the matrix then gives problems. So let's just say that there are no isolated nodes. Okay, so clearly, how I'm writing this matrix, right? L was positive semi-definite. D, right? I'm hitting it with a matrix on each side, so clearly this matrix is also positive semi-definite. So some properties about this object. So L of G is clearly positive semi-definite. And again, we're going to order its eigenvalues, right? In the same way, going from the smallest to the biggest, right? It's good to keep in mind. I mean, I like trying to keep in mind a few things. Always one, the sizes of the matrices we're dealing with. That's always very useful. But also, where are the important parts of the spectrum? Right, so here the important part of the spectrum, remember, the Laplacian was close to zero, was the smallest one. And I mean, I didn't invert anything here, so it will also be the spectrum close to zero. Now, of course, this matrix will also have an untrivial kernel. There's also something in its kernel, right? So in particular, it's easy to see that if I take d to the 1/2 times the whole one's vector, right, that this is in the kernel of the normalized Laplacian, right? Because if I take, maybe it's worth doing this calculation. If I take L of G of d to the 1/2 of 1, I get what? I get d to the minus 1/2, L of G, d to the minus 1/2, d to the 1/2, 1. These guys go away, and I get LG of 1, which is equal to 0. Right? This is just a proof of that fact. Okay. So we know some things about this object already. Let's order its eigenvalues again. Oh, sorry, first one. G. So here we know maybe a bit more. Okay, all the way to n. Okay. So now, now I'm going to state the theorem, right? And then we'll prove it. And so I'll state first the theorem so that so that you see what we're going to prove, and then I'll sort of intuitively build up to it. Right? So here's the theorem. Okay, so we're going to prove the following theorem, and this is what we're going to do on the first half of today, and maybe we'll spill a little into the second. Okay, let G be our graph. Right, again, right, without, let's say, without isolated nodes. Right, and LG, the normalized graph Laplacian. Right, maybe notice that, right, because L of G is D minus AG, this is really just identity minus D to the minus a half times adjacency, D to the minus a half. Right, so the eigenvalues of this are just 1 minus eigenvalues of this normalized adjacency, but it's more helpful to consider this Laplacian. Okay, then the following holds, right? So an inequality of the style of what I promised. The second eigenvalue, G, is smaller or equal than some notion of cut, right? Of how disconnected. So we take the minimum over all non-trivial sets, subsets of nodes. Okay, and then what we're going to consider here is cut of S. So cut of S is the number of edges that get cut between S and S complement. I think I defined this at some point. Maybe I'll write it again. Okay, so we're going to prove this. Okay, a few pointers in case in case you don't remember this definition. So cut of S is the number of edges that get cut, the number of edges between S and S complement. We can write it as sum over I in S, sum over J in S complement of like the indicator that IJ is an edge, right? One if it's an edge or not. It's just counting how many edges go from S to S complement. And volume is just a measure of the size of a set. But it makes sense to measure the size of the set not by the number of vertices, but by the number of edges that are incident on the vertex. Okay, so volume of S equals sum I in S of degree. Right, so it's just counting how many edges are incident on the set S. Okay. Okay, another pointer. This thing oftentimes is called the normalized cut, right? I mean, it doesn't matter really what it's called because I'm gonna switch to another type of cuts, but this is often called the normalized cut. Shows up often in spectral graph theory literature. Right, it's often called a normalized cut. Okay. So before we prove this theorem, let's get some intuition. So what's this business of having this having this volume divided by the volumes, right? It's sort of strange. Why are we not giving a bound straight away in terms of cut? So measuring how good of a partition is, right? If we split a graph into a set S and a set S complement, right? We really want to count how many edges go across, right? This is cut of S. But if we want to say that the graph is as a geometry that tends to corresponds to something that's very disconnected, then sort of what we don't want is to have like just one point being the set S and the rest being S complement, right? And then of course this point is not that connected because I mean, why would it have that many edges? There's only one node, so maybe it only has two edges, and so this cut, right? It is indeed the cut is very small, but it's not really meaningful about the geometry of the graph. Like this graph, right? If let's say that all the here are all very lots and lots of connections, right? This one is much more like the geometry of two separated pieces than this one is, right? And so this n cut, what it's doing, right? N cut promotes balanced cuts because you're dividing. you're taking the sum of 1 over volume of S and volume of S complement. If one of these volumes is very small, then the end cut is very small. So end cut promotes more balanced cuts. So in fact, if you are looking for a graph to try to cluster it, to find partitions of it that have very few edges in between, this is what you should be looking for. You should really be looking for balanced cuts. So you should really optimize something like the normalized cut and not just the cut, because otherwise you risk getting into issues like this where you're putting out nothing on one side or just a node or something like this. Okay, so in fact, this is the kind of cuts that we want to consider. Okay, any questions before we prove the theorem? Okay, so now we're going to prove it. Okay, I mean, it's not going to be a direct proof. Like I'm going to explain a few things and define a few things throughout the proof, and maybe have some propositions inside the proof. But I mean, we're now ready to start the proof. Okay. So the idea here will be that of relaxation, and this will become clear in a second. Okay. So let's write, right? So you saw in one of the homeworks this Coren-Fisher, variational principle of eigenvalues, right? So we have in particular that the second eigenvalue, because the smallest eigenvalue is the right. We know it's in the kernel. Is this d to the 1/2 1, right? And the value of the second eigenvalue will be the minimum, right? And if you've never seen the proof of this, you should try to do it. Okay? The minimum eigenvalue will be equal to the minimum, right, among all vectors of norm 1, and orthogonal to the smallest to the eigenvector associated to the smallest eigenvalue of the Laplacian, right? And then the quadratic form. Okay, so this is what the second eigenvalue is equal to this, right? This follows from the, sometimes it's called Coren-Fisher. Assuming you saw this in the linear algebra class, variational principle of eigenvalues. But I mean, it's if you've never seen it, try to spend some time trying to prove this principle. It's if you take the spectral decomposition and so on, it's not so hard. Okay. So what is the right? So what is this V1? This V1 of LG, we know what it is, right? It is d to the 1/2 all one's vector, right? This is the vector that's in the kernel. Okay, so now the idea, okay, the trick will be, the idea is this idea of a relaxation. Okay? And this will become much more clear in a second, but let me already sort of give a bit of foresight of what's going to happen, right? So we're going to show that the second eigenvalue is smaller or equal than this quantity. Okay. Now the second eigenvalue is the minimization of this type of quantity, right? If it wasn't for the fact that it's a normalized Laplacian, what we would have here, if it was a normal Laplacian, we would have something like a sum of yi's minus yj's, right? And so what this normalized cut will be also the minimization of this, but restricted to only special vector z. Right? And this makes sense because if I have this sum of these yi's minus yj's, if I restrict yi's and yj's to take only a value, say 1 in S and minus 1 in S complement, then this is indeed counting the cut, because the only time that this square inside the sum is non-zero is when I'm taking an edge that's being cut. So the same way, I mean, we already saw this in this proof that the eigenvalue was 0 if and only if the Laplacian had if the graph was disconnected. But here we're going to get something much finer, right? That basically this normalized cut will correspond to minimizing this object, but only over a special smaller set of S's. And because we're minimizing this over a smaller set, of course, the minimum needs to be bigger, right? This is going to be the idea. Okay? And so it's going to be very helpful to write, right? Because we want to understand this quadratic form, it's going to be very helpful to write things in terms of the Laplacian and not the normalized Laplacian. So the normalized Laplacian is the right object to define these eigenvalues to get this relationship. But in the proof, it will make a lot of sense to go back to the Laplacian, right? So how do we go back to the Laplacian? Let's now do a change of variables, right? And let's take y being d to the minus half z, right? So like change of variables. I mean, that's basically what it is, change of variables. Okay, but let's see what this change of variables gives us. So with this change of variables, we have that lambda 2 of L of G, right, is equal to the minimum. Okay, so now what are the properties of Y? Maybe I should write them here. Okay, what are the properties of Y? Well, Z being equal to 1, right, is the same thing as Z transpose Z being 1, which is the same thing as now, right? So, okay, let's do the change of variables like a bit more carefully. So Z is equal to D to the 1/2 Y. So Z being 1 is the same thing as asking that Y transpose DY is 1, right? I need to do the change of variables also in the, right, in the constraints. And um, Z being orthogonal to V1 LG, right? And we know what this vector is. It is D to the 1/2 1. This is the same thing as Y transpose times D a half, D a half, I get a D, orthogonal to this, right? Okay, I'm just rewriting the constraints in this variable Y. Okay, so now I have minimum over Y satisfying Y transpose D Y equals 1. Y transpose D1 equals 0 of, now what do I get? Y transpose D to the 1/2 normalized Laplacian, right? Because this is Z transpose, right? D transpose is the same as D because it's a diagonal matrix. D to the 1/2 Y. Okay. Now what was the normalized Laplacian was when I multiplied by D to the minus half on both sides. So now since I'm multiplying by D to the half on both sides, they just cancel out. Okay, so now I'm having a very nice object. So I have minimum Y transpose dy equals 1. Y transpose LGY. All right, but what is this? This is the minimum over Y transpose dy equals 1. Y transpose d1 equals 0. And what is that? Is the sum of I and j in the edges of yi minus yj squared. Okay. Okay, but now if I want a cut to show up, right? If I want to measure something like a cut, then it makes a lot of sense for me to ask now to restrict this quantity only for vectors y that take two values, take a value in S and take a value in S complement. Right? So now there's going to be an idea. So idea, we're going to restrict to vectors y taking values, taking only two values. Right? What do I mean by this? I mean yi for a set S. Okay? Again, I always want my set to not be trivial, right? So it shouldn't be the identity or all of the nodes. That's not interesting. That yi takes the value A if I is in S and takes the value B if I is not in S. And now I'm going to restrict over these vectors. Okay? And we're going to see that once we restrict to these vectors, we're going to get exactly the normalized cut. Okay, so now there's a fair amount of calculation, some of which I'm going to defer to as a challenge, some of which I'm going to do, right? Because now there's okay, the idea was this is an important idea, but now we have to compute, right? We have to do two things, right? We have to say for which, right, for which values, right, for which values of A and B does Y satisfy the constraints, right? There's two constraints that Y needs to satisfy, right? Y needs to satisfy Y transpose dy equals 1 and Y transpose d1 equals 0. It's two constraints to two variables, A and B. There's going to be a unique solution. I mean, a priori, it's not obvious because this is not necessarily linear, but in this case, it's okay. And so we need to ask ourselves that question. Okay, so this was left as a challenge, but it's kind of it should be right. Okay, it's just a calculation now, right? Because once I do things like Y transpose dy equals 0 equals 1, sorry, like what is this? This is just what is this? This is the sum from I from 1 to n, right? Of yi squared degree of I. Right? And this sum has two types of terms. Has the terms where I is in S and the terms where I is not in S. Right? So this is equal to A square when it's in S times the sum of I in S degree of I. Right? But what is this? This is equal to the volume of S plus B square times the sum when I is not in S times degree of I. But what is this? This is just the volume of S complement, right? So the equations that they need to satisfy are quite simple. We need to have a square times volume of S plus B square times volume of S complement, right? Given S and S complement, A and B need to satisfy this equals to 1. Okay, and the other constraint is also not hard to see. It will be something like A volume of S plus B volume of S complement needs to be equal to 0. And so now, right, I think, so, I mean, maybe we should do it. So I get Y transpose D1. Okay, so this is constraint number 1, or yeah, constraint number 1. Let's look at constraint number 2. It's Y transpose D1 equals 0, right? But what is this? This is sum from Y from 1 to N, right? What do I get? I get, right, this is diagonal, so I only pick up the diagonal term, so I get the sum of yi times 1 plus yi times 2 plus yi times, no, sorry, y1 plus times 1 times the degree of the first node plus y2 times 1 times the degree of the second node and so on and so forth. So what do I get? I get degree of I times yi, right? And what is this? This is just same thing, right? I get a bunch of sums of different types. So I get now A times volume of S plus B times volume of S complement. Okay, so this is the second equation that it needs to satisfy, right? So second equation is that A, okay, and this will have only one solution. Well, okay, of course, for A and B, if I take minus A minus B, it's also a solution, right? Because taking Y or minus Y will be the same thing. But aside from that, there's only one solution. Okay, so rest will be left as a challenge, how to work out what the values are. But it's literally just solving these equations, right? Two variables, two variables, two equations, and you get the following. You get that the vector y needs to be of the following type. So I'm just going to write it out. Okay, I just want to convince you the calculation is easy, but there's no need for me to spend much time doing it. Volume of G. I didn't get anything wrong. Square root. Volume of G is just the volume of all the graph. It's a bit of an abuse of notation, right? It should be volume of V because we define volumes of sets of nodes. But this is a common abuse of notation to use the volume of the whole graph. Okay, So this will be the vector y. So what I mean by this, if I is in S, if I is not in S. So we will resort to these special vectors. Okay, but see the rationale here, right? We decided we're going to look at vectors that only took two elements, because then they're really measuring a cut. Now we said if they take only two values, those two values are sort of determined, right? Because they don't really have any option, right? Because they need to, right? They need to satisfy these constraints, that there were these two constraints and we had two of these variables. And so now we saw that they need to be this. So now what we need to compute, right? So we need to compute. We need to compute y transpose L G Y. Because this will be the value of the quadratic form for these vectors. So then once I minimize over all possible choices of set S, I get the minimum over all possible choices of vectors with two entries, with only taking two values as entries. Okay. So now, okay, so let's do this. Now comes a calculation that this one is worth doing because it's non-trivial. Okay, so I just realized there's a typo in the notes. There was a half here that is not there. This is because sometimes another notation is used in which edges are counted twice, but it's not the case here. Okay. Okay, but now what's the idea? Now we know that y depends only, the value of I depends only if y is in S or not in S. So the only terms that show up here are the terms where, right, only terms where I and J are, one is in S and the other is in S complement show up, right? And because we only count each edge once, we're going to count the edge, only the edges that cut S and S complement show up. And we're going to count with I being in S and J being in S complement, right? We could count some edges that way and some edges the flipped way, but since we're only counting them once, we can pick. And so I claim this is the same as taking I to be in S, sum of J not in S or in S complement. Okay. 1 of ij, right? So this is the indicator function. It's 1 if it's an edge, it's minus 1 if it's not an edge, of yi minus yj. Right? So far so good? Everyone still with me? Yeah, I didn't really do anything, right? When they are in the same set, the value is 0 because y takes the same value, okay? Now, if they are in different sets, if I take the, okay, second claim, this number is always the same thing because yi for I is S is always the same and yj for j in S complement is always the same. So this is always exactly the same value. Okay, so let's do that. Okay, now comes a bit more, it's going to get a little nasty, but it's okay. We'll simplify right up. Okay, so what do I have here? Okay, I get the square, and now let's be brave. I get volume. Okay, maybe I'll go up a bit so that I can see. Right, I'm just putting those numbers up there. Volume of S complement, volume of G, right? And now I take square root minus, but because it has a minus, is really a plus, right? Because of this minus here. I think maybe this is the kind of calculation. I mean, it's not trivial, but it looks more difficult watching me do it than probably just trying to do it yourself. But it might still be useful for me to do it. Okay, I mean, now you collect terms basically, and there's like a trick. Okay, so it's kind of a cool trick, so let's do it. So, okay, so first of all, this term, let's simplify this already a bit. So this term here, right, is something, and I mean, I can take it outside of the sum. right? I can move this term outside of the sum, right? Because it's the same for every I and j. Okay. On the other hand, this blue term, this sum now, right? This blue term is just equal to the cut of S, right? Because this is just counting how many edges get cut, and each edge gets cut gets a value of this thing in red, right? So if this is too fast, please interrupt and ask questions, and I'll explain more. But so now I removed all the sums, right? I have cut of S times now this ugly expression, right? Okay, let me write it. It's complement volume. Maybe I'll open up the square now. Okay, so I'm going to open the square up. So it's the first term squared plus the second term squared, or let me say that twice, the plus twice the product of the two. Okay. Okay, I made a typo. Let's see, because it's supposed to be an S complement and an S. Where does this typo go? Oh, it was just here. Okay, so it was just, the typo was just, is just isolated in this expression, and this should be S complement. Okay, yeah, okay. See, something was off, because there's some cancellations need to happen, thankfully. Volume of G, let's see, 1 square root. Okay, let me just already cancel. Okay, I won't. I'll do it later. Okay. You're seeing already that there's a lot of stuff that's canceling, but okay. Plus the square of that term, volume of S over volume S complement volume of G. I mean, this looks a lot worse than it is. Okay. All right, so now let's cancel terms. Great. Okay, this guy cancels with this guy. Okay. This guy cancels with this guy. And this guy and this one, right? Square root, so becomes 1, and this one can go outside. Okay, so let's make this a little nicer. This is equal to cut of S over volume of G. Or it's actually more useful maybe too, because I'm going to use this volume term to cancel something else later. Okay, so it's a bit more useful to keep it like this. Cut of S, 1 over volume of G. And now what do I have? What are the terms that survived? There's a volume of S complement over volume of S. There's a 2, right? Just a number 2, everything else went away, plus a volume of S over a volume of S complement. Okay, now comes the algebraic trick. So far, there's no trick. Now comes a cool algebraic trick, which is to notice that this 2 is nothing but, right? I can write this as volume of S over volume of S, because that's 1, plus volume of S complement over volume of S complement. Right? 2 is equal to this. Right? 2 is definitely equal to that. And so now I can send them to each one of their respective fractions, right? Because now I have cut. Okay, and I'll end this calculation and then take the break. Sorry for that, 2 extra minutes. Volume, and now what do I have? I have volume of S complement plus volume of S over volume of S plus volume of S complement plus volume of S times volume. Okay, but now we're there, right? Because this is the volume of S plus the volume of S complement is clearly equal to the volume of the whole graph. Same thing here. And so they cancel with that term down there. And so this is just equal to the cut of S times 1 over volume of S plus 1 over volume. That's a magical cancellations. Right, and this was exactly our definition of n cut. Okay, so we're done with this part. Now we need to finish the argument, but I don't want to get into go over the break as little as possible. So let's all take a break, and we'll be back at 5:15. Okay, I'll stick around if there's any questions.